Hello everyone, this is a comparative study of bracing patterns and materials for tall timber buildings. We are expected to reach a global population of 9.7 billion by the year 2050, with 68% of the population predicted to live in urban areas, increasing the demand for newly constructed tall buildings. The construction industry is a major source of global carbon dioxide, with cement and steel being the most commonly used materials and leading contributors to the global carbon emissions related to construction. However, recent technological advances have enabled versatile applications of engineered timber, which is a renewable material that uniquely sequesters carbon dioxide. Unfortunately, mass timber is neither a commonly considered option in the design practice, nor is it supported by many of the local building codes. Traditionally, wood has been mainly used in light frame construction, but mass timber technology has recently shown the potential of timber to be a competitive alternate material to steel and concrete. Two notable recently built tall timber structures are located in Norway and seen here, Treat and Mjøstarnet. Treat is a 14-story timber building with mega glulam bracing on the perimeter that alternates with stiffer transfer trusses. Mjøstarnet is an 18-story structure using perimeter glulam bracing and large corner columns that support both the compression and tension forces. Both of these structures use perimeter bracing, which is a very structurally efficient lateral force resisting system. A notable DIAGRID structure that uses perimeter bracing and inspiration for the structure analyzed in this presentation is the Hearst Tower in New York City. This system places the bracing on the facade to bring the weight of the building into the bracing system, which benefits the lateral resistance of the structure and accommodates the use of lightweight timber material, which performs well in compression. The objective of the present study is a comparative analysis of structural performance and carbon costs of perimeter bracing configurations, which is based on a strategy of integrating bracing geometry with the placement of glue laminated timber and steel, the two main structural materials. To begin, a topology optimization problem was formed. Topology optimization is used to optimize the layout of a material for a given design space, loads, and boundary conditions. This was formulated to anticipate efficient spatial arrangement of elements in a cantilever structure used to represent a high-rise building subjected to a transverse load or wind load. This is a continuum topology optimization problem that uses the density-based approach and is formulated to achieve maximum stiffness of the building. This method was carried out for an isotropic material, steel, and for an orthotropic material, timber. The resulting material distributions for the elements shown are consistent with material characteristics of steel and timber. For steel, the material is placed symmetrically with respect to the vertical and horizontal axes, which is expected for an isotropic material. For the timber, more material is placed vertically or along the strong axis, which is typically along the grain of the wood. The optimized solution for the timber design problem demonstrates a layout similar to a steel braced frame, but with larger modules created from solids and voids that look like mega bracing or high-waisted bracing. Using these results, various mega bracing topologies were created to analyze the relative stiffness of timber and timber-steel hybrid lateral systems. So these additional hybrid configurations of bracing were created to explore the effects of placing steel and glulam elements at multiple locations around the perimeter of the structure. As seen here, we explored structural performance based on the mega bracing material and on placing steel in the vicinity of building corners. All layouts were modeled in 3 dimensions using blue ball RFEM and analyzed for the loading conditions specified in the relevant building codes. The layouts were compared based on their relative stiffness, total weight, and embodied carbon of the structures. The potential advantage of using hybrid systems is for a specific material to be placed where it performs best or where it can compensate for the weakness of another material. If this were an optimization problem in pursuit of the stiffest lateral system, the result would prove to be all steel. And if it was in pursuit of the lowest weight, it would be all timber. But the objective for the present study is to quantify the potential savings in the embodied carbon through structural design. Therefore, the various layouts were analyzed and compared in terms of their structural performance and carbon impact. These models have 28 stories with a height of 4.3 meters per story with a total of 120 meters. 2 add-on modules from RFEM were used to optimize the members of each module, allowing for the smallest member sizes to be chosen without exceeding the strength and serviceability limits required by the building code. The layouts 5 through 8 shown here were created to investigate how the system performs when multiple bays of bracing have various percentages and locations of steel and timber. An extra bay was added in these modules to create opportunities for hybridization and investigate the behavior of the structure when steel is placed towards outer edges where the axial forces are expected to be higher. This figure shows the resulting embodied carbon in the bracing layouts and the relative contribution from timber and steel members. Layouts 1 and 5 resulted in the lowest embodied carbon, and layout 4 had the highest total value with the most contribution of steel. The difference in behavior between designs 2 and 4 is of interest of a future study. The multiple bay hybrid layouts 6 through 8 have overall low embodied carbon due to a small contribution from timber, proving the effect and importance of the structural geometry. In this study, the main focus is on the structural and carbon efficiency of different bracing patterns relative to their geometry, element material type, and material placement. The figure on the left shows performance to weight ratio for each model as a relationship between the tip displacement and the weight of the structural elements. We find that the designs 1, 3, and 5, which are only or mostly composed of timber, result in the lowest structural weight and greatest tip displacement. The cluster of hybrid designs 2, 6, 7, and 8 provides insight into potential geometries and material placement that can lead to relatively similar performance. Design 4 uses the most steel and leads to the lowest drift for the highest weight. The comparative analysis of different layouts shows how the distribution of forces is geometry and material dependent. The all-timber layouts of diagonal bracing have proven to be feasible designs by meeting the design requirements. We expect that the geometric arrangements which allow loading the timber elements predominantly in axial compression when its strength compares well to steel and concrete could further improve structural efficiency. Ultimately, it is up to the design team to decide whether to propose timber as a structural material. While its use can reduce carbon emissions, the element cross-sections that are large relative to steel may not be desirable depending on the design intentions for a specific project. The performance to weight and performance to carbon ratios associated with single material and hybrid designs in this study point at future opportunities for structural design of new buildings. Despite the potentially higher construction or material costs and the particular mechanical properties of timber, it is worth employing thoughtful engineering approaches to understand the best way to construct with it. The workflow established here can be helpful to structural engineers as they begin to design more with timber and aim to understand how it behaves as compared to steel, which is conventionally used in engineering practice. As we continue to build higher, we need to be conscious of the future carbon footprint related to the construction industry and the potential of timber to contribute to sustainable solutions. Thank you.